Okay, so late last year we published a paper on alkyl group inductive effects, and it has quite a few implications. So the conventional wisdom has been that alkyl groups exert an inductive electron donating effect. What we've been able to show is a range of methods, mainly computational, but we've also compared it with experimental data, is that actually the inductive effect is electron withdrawing. And it's such a small effect. So what I want to do in this short video is talk you through some of the implications of this, and particularly focusing on the implications for the A-level curriculums of the various exam boards within the UK. So I'm going to start with a couple of simple molecules, and I'm going to build it up. The first bit is a little bit of extra detail that isn't directly relevant to the A-level curriculum, but I think it's a good way to set the stage. So let's start with water and methanol. So we've replaced a hydrogen with a methyl group. Whenever we talk about alkyl groups being electron withdrawing or electron donating, we're talking about a comparison to hydrogen. So we can't actually measure the charge on an atom. It's quite a nebulous property. There are a number of ways to calculate it using quantum chemical calculations, and they'll all give you slightly different numbers. In general, they all show you the same thing. And what they show you is that the charge on that oxygen atom is slightly less negative or more positive. I'm not saying it's got a positive charge. We've got oxygen atoms here with, in both cases, with 2 lone pairs. This oxygen is less negative than this oxygen, and what that means is that the difference between H and methyl, if the methyl reduces the charge, the negative charge relative to the H, then the methyl is electron withdrawing, and it's a really small effect. To put that into context, with the method of charge calculation that we prefer to use, it equates to a difference of about 0.05 or a 20th of an electron. It's a small shift, but it is significant, and it's significant because most of the textbooks that you encounter will tell you that a methyl group is electron donating relative to hydrogen. In our paper, and I'll put the link in the comments, we look at why people believe that, and it's based on experimental data that has been discredited. Okay, so now let's have a look at what happens if we protonate the oxygen. Okay, so we've added a proton. In this case, we've got the hydronium ion. Here, we've got protonated methanol. Now we see a difference. And what we find with this ion here, we'll have a charge on our oxygen atom, and we've got an equal charge, so an equal amount of positive charge on each hydrogen atom. What we now find in protonated methanol is the total amount of positive charge on the methyl group is slightly higher than that on each hydrogen. What that means, if there's more positive charge on here compared to here, is that is donating more electron density. I'm not going to put numbers in. So methyl in this case is electron withdrawing, but here it's electron donating. Now the difference is the positive charge. Let me add some more structures over here on the left, and what we're going to do now is deprotonate. So we're looking at hydroxide versus methoxide, and in this case the amount of negative charge on the oxygen is lower here than it is here. and it's a bigger effect than we see here. So this methyl, if we take the simple view, the methyl in the middle, neutral, it's electron withdrawing, but it's an incredibly small effect. When we put more electrons on, the methyl becomes more electron withdrawing. It's got more electrons to withdraw. But when we take electrons away, when we protonate the oxygen, the methyl becomes electron donating. So in historical terms, Ingold proposed a term for this. Instead of inductive, which is what we've got in the neutral molecule, he called it an inductomeric. Now we don't use that term anymore, but the term that we can use is polarizability. So instead of this being an inductive effect, a methyl group has more electrons, and you can just think about it, that this positive charge here is pulling those electrons towards itself. And there are more electrons to pull towards itself or to polarize in a methyl group compared to a hydrogen. Similarly, this methyl group here is able to polarize the negative charge towards itself. So it can respond to the charge. It can either give some of its electrons to a positive charge or absorb some electrons from a negative charge. So the reason for the redistribution of charge here is not inductive, it's polarizability. And that's really, really important. So now what I want to do is come to the classic A-level example. And that is amine basicity. So if we have ammonia and methylamine, we know that methylamine is a stronger base than ammonia. So we know if we add an acid, then this is more basic, which means that equilibrium is further towards the ammonium salt than we get when it's just NH4+. So here's the conventional explanation. The reason, now this is wrong, okay? The reason why the methylamine is more basic is because the methyl group donates electron density to the nitrogen that it can then pass on via its lone pair. We increase the electron density at the lone pair. That is not correct. If we look at the charge distribution in ammonia and methylamine, and we've done this and we're about to publish it for a much bigger series of amines, other people have measured the basicities of various amines, and they've also looked into the reason. So what I'm saying now is not controversial. It's pretty well established in the research literature. The bit that's new is the pretty clear evidence that in line with the other data, the amount of negative charge on the nitrogen here is lower than here. So the methyl group is not donating electron density, it's actually withdrawing it. But exactly the same as I've just explained with oxygen, what we get is a methyl group here withdrawing a little bit of electron density, but here this methyl group is polarizable, not strictly an inductive effect. So it's donating electron density to stabilize the positive charge in the ammonium. So the idea of electron donation, electron withdrawal is really, really important, but what we've really got to be thinking about is the relative energies of two species. So if I just label this as RNH2 and RNH3+, if I want to move that equilibrium over here, I can do one of two things. I can either move that down, or I can move that up. Or there are permutations. If I move that up a lot and that up a bit, we get the same effect. What we're looking at in terms of our equilibrium constant is an energy difference here, and that's the really important thing. Electron withdrawing or electron donating is quite subtle, but we can think about it in terms of stabilizing that positive charge, and it's the polarizability effect. It's this side of the equation that we're affecting. It's not an effect in the neutral amine. So in terms of what you know, I'm not the person to say exactly how this should be taught at A level. It needs a little bit more consultation, but what we've got to do is ensure that an explanation isn't given that has been demonstrated to be factually incorrect, and that is the methyl being electron donating. So methyl groups will stabilize plus and minus charges by polarizability effects. Now there's one more thing in the A-level curriculum, and that's carbocation stability. So I'll get rid of this. So if we use the example that's most commonly taught in the A-level curriculum, if we add HBr to propene, then what we get is this, and what we're doing is we are adding H plus, and we have a choice. We could either get this or this, and this secondary carbocation is considerably more stable than the primary carbocation. Therefore this is what happens, and then a Br minus attacks here to give the observed product. So we're getting the most stable intermediate. Now we explain carbocation stability at A level using an idea called hyperconjugation. It is donation of electron density from the methyl groups in this case, but it's not an inductive electron donation. It is a very specific molecular orbital effect involved in the carbon-hydrogen bonds. But what we could perhaps think about it at this level is it being the same as polarizability. So we've got stabilization of a positive charge on an oxygen, polarizability, stabilization of a positive charge on a nitrogen, definitely polarizability, although there is some argument that there are orbital effects within that. And we can use that same explanation as a simplified version of the hyperconjugation effect that is a more detailed rationalization. So it's all, for me, it's all about identifying the things that aren't correct, and I think this is just venturing an opinion. If we tell students that the methyl group is electron donating inductively on nitrogen, there would be the temptation when we say that this with more methyl groups is more stable than this with an ethyl group, there's a temptation to generalize this to alkyl groups are electron donating. So I guess the take-home message is alkyl groups can be electron donating, but it's not an inductive effect. That is, it's not in the ground state in a neutral molecule and due to electronegativity difference. If we want to think about the electronegativity, then carbon has an electronegativity of 2.52, hydrogen has an electronegativity of 2.2. So carbon is more electronegative than hydrogen, and without going into too much more detail, it may be that that's not the best measure. I know we think about electronegativity a lot, but it's not actually defined as in terms of an electron withdrawing effect. It's defined in terms of bond dissociation energies, so it may not work perfectly in all instances, but as a simple measure carbon is more electronegative than hydrogen, the inductive effect is absolutely, definitely electron withdrawing in a neutral molecule. And as we saw at the start, in a positively charged molecule we can have a significant electron donation effect. In a negatively charged molecule we can have a significant electron withdrawing alkyl group effect. So we have to focus our inductive effect definition on the neutral molecule, otherwise we can pick and choose what an alkyl group does. And unfortunately that's the more complex reality of the situation, which is why we should always focus on polarizability or hyperconjugation arguments in charged species, and those tend to be bigger effects than the pure inductive effect in a neutral molecule. I hope this is useful.